Is quarter 4 going good for you though? Have you been able to stay on top of it?
Yeah.
Good.
It's been going okay.
Good. All right, so today we are going to be talking about work, right? So we know that this unit is going to be about work and power, and let's go ahead. We are going to have a couple of announcements, schedule reminder, then we're going to get into our warm-up, and we're going to talk about work, and then we're going to talk about power. So look, this image is an example of what we mean by work, okay? So just keep this in mind. There's going to be lots of kind of examples of this. So announcements, we, like I said, make sure that you're staying on on the due date for this quarter. We may not have access after the quarter ends, so we may not have access to Fuel Ed afterwards. So it is really important that we keep on top of the pacing guide. So this is the pacing guide for this week. One small change. I changed unit lesson 2.6 to be on the 6th on Thursday. Instead of on Wednesday, because these two labs to me seem like they go more than separating them. So because these are the two labs. So I put the labs on one day, and so on Wednesday, tomorrow, you only have one lesson to do. Okay, so that's one small change from this image, and I already reflected that in the pacing guide on the due dates for the plan. This is my schedule. I just have a couple of things that need to change. On Thursday, I offer one at 11 instead of on Friday. So there's one or at 9:30 here. Yeah, 9:30 instead of at 11 on Friday. So just so you know, there's 2 small groups on Thursday. So today we are going to be defining work. We're going to be calculating work. We're going to explain work and then connect the work formula with a graph. So that's kind of what we're going to be focusing on today, really getting into the weeds. So let's start with our warm-up, and you can put it in the chat or you can answer it out loud. What do you already know about work? What are some things that you already know about work? And we're not talking about the work where you go in and you make money, right? Or a job. We hear this word all the time, but what does it mean in the physics world?
Is it when like work is only like work when like something's being moved or some sort of like force or energy is on it or something?
Oh, yeah, good. Okay, so it has something to do with movement, has to do with force, has to do with energy being used. Good. Yeah, Abby, any other ideas? Anything to add?
I thought it was like the movement of like lifting or like pulling in like some kind of direction. But then I also thought like if you lifted something up and just kept it there, you wouldn't be doing work. You would be doing work if you pushed it up or like lifted. I don't know, that's what I thought.
Yeah. Oh my gosh. Okay, we can end class early. You guys got it, right? That was awesome. That was really, really good. Yes, something to do with movement, something to do with force, something with push or pull, right? We know that there's going to be something to do with energy. That's awesome. So yeah, that's all we're going to talk about today. So remember, we need to also keep in mind a couple of things. Newton's laws are one of those things where it's like the basis of physics. Things have been really built on top of Newton's laws. So remember that an object in motion stay in motion unless acted on by a net force, right? So that is actually Newton's first law, right? An object in motion stays in motion until another force is acted upon it. And this time, we're really thinking about this as a net force. We're taking a look at the different directions and we're finding out the difference and seeing in which direction it's actually going to be going into. So that net force is underlined because that's what we're going to be focusing on when we talk about these forces. Also remember that a net force produces acceleration. Okay, so whenever there's a net force, whenever we're pushing something, pulling something, we're changing that object's acceleration, meaning we're changing that velocity or motion. Acceleration is the change of velocity over time. So remembering that when we push an object, we're producing acceleration. It's going from rest to a different speed. That's a change in velocity. We also want to remember that acceleration or the change in motion happens over a period of time. The faster you change the velocity, the higher the acceleration, right? Think about this in a car. When they talk about in 60, it can go from 0 to 60 in 2 seconds versus 0 to 60 in 10 seconds. That's a different acceleration, right? So remember, the shorter amount of time it goes over, the higher acceleration. Distant changes over this period of time. So remember that in addition, it's also covering a certain amount of distance. When you are pushing something, not only are you changing the speed over a time, but you're also you're moving it from one point to another. So there is this distance that is also being covered. So there are quite a few things to remember. Do you guys have any questions on this so far? Thinking about these individual bullet points before we get into mixing all of them together. Are there any questions? Okay. All right. So we are going to talk about work. So work is a measurable quantity, something that we can actually calculate. And it's done when a force acts on an object and causes that object to move in the same direction of the force. So this is where I think you were getting at, Abby. So Madeline and Abby, your two answers to the warm-up was perfect if we combined them, right? Madeline, you focused more on moving something, putting in a force, right? You talked about lifting something. Abby, you put in something to do with moving in the same direction. You brought up the idea of direction as part of it as well, which is absolutely correct. So remember that the movement needs to be in the same direction of the force, which is why, Abby, you were talking about when you lift an object and you hold the box, when you lift the box and it's moving into that same direction of the force that's being applied, which is you lifting it up, right? Vertically, it's moving vertically, therefore work is being done. But once you're holding it and you walk across the floor, that's not work being done because your force is not moving in the same direction as you, right? You're holding the box, but you're not forcing the box. You're not putting any more force on it to go across the floor. You're putting force between your feet and the floor, but not the box. So there is no work being done on the box anymore. So you guys were doing a great job at combining your answers. It would have been spot on. So good job, you guys. So we have this equation. This equation is work is equal to force times distance. Okay. Remember, there's this big note that force must be parallel or in the same direction as motion. That's a really big thing when we're talking about work. And that's exactly what I was saying with the whole lifting up the box versus walking across the floor with the box, right? We've got work, W, force, distance, and then we use this unit. So we have this Newton times meters is what stands for joules, but we use joules as our unit when we're talking about work, when we're talking about power. If you were to break it down, it really is just Newton times meters. Okay, so we use joules when we talk about work. Questions on this page. We're going to get into some examples on the next couple slides. Okay. So when is work being done? Again, right, when objects move in the direction of the force. Pencils, you are working on the pencil. You are forcing it across your paper. You're putting force on a pencil. As you write across the page, you're doing work, right? The force that you're pushing the pencil is going in the same direction. But no work done is when there's no movement or the direction of the force and the direction of the movement are different. Okay, so if they're not going in the same direction, if you are pushing a box across the floor, you're doing work. If you're picking it up, you're doing work. But if you walk across the floor, but there's no additional force on the box, then you're not doing work, right? I'm going to leave this slide up for just a couple of minutes, let you guys write this down. This might be a good thing to write down just so you know if you get confused. Because there are times where you're like, wait, I just got so confused. Is this work? Is this not work? Coming back to this T chart will be really helpful to kind of remind you. There's going to be a little bit of, like, when you're working through these examples, you're going to need to really want to visualize it. There's going to be a little bit of visualization of the actual concept or the situation. So that way you can determine whether the movement and the force is in the same direction. Hmm. Let me know when you guys are done writing it down, and then we'll move on.
Okay, I'm done.
Perfect. Thanks for letting me know.
Okay, I'm done.
Perfect. All right. So now we know when work is done and when work is not done, right? Direction of force needs to be in the same direction of movement. Bottom line. Great. So who has done the most work? So now we have two situations. We're going to go ahead and solve who's done the most work by going ahead and figuring out what our work is, right? So we've got our equation, which is work is equal to force times distance, okay? So we have something happening over here where there's no movement. For 10 seconds, this object is 300 kilograms. This person is applying 500 newtons of force. And then we've got this scenario where this person is applying 500 newtons of force on an object that's 100 kilograms. It traveled for 6 meters over 5 seconds. So who has done the most work?
Would it be the guy with the orange ball?
And why is that?
Because the other one says no movement, and so it has to have movement to be work. Sorry, Abby, got to it first.
No problem. Yeah, you
My
got
answer
it.
would have been wrong.
Well, that's okay because it's confusing, right? Because this is still an arrow that's showing it, right? But yeah, Maddie, you're right. So this one is going to have the more work because there is movement, right? This one is too big. It's too heavy. They're not going to be able to overcome that force, right? So remember that this amount of newtons needs to be bigger than this amount of newtons in order for you to be able to move it across the ground. Good. Good work. All right, let's see. So, right, exactly. So 500 newtons times 0 joules, whereas 500 newtons times 6 meters is equal to 30,000 joules. Good work, you guys. Okay, work in the direction of motion. When work is done in the direction of motion, we also think of it as work is equal to the change in the kinetic energy. Now, we have not talked about specifically energy yet. So remember, energy, there's two main types. We can put it in as potential energy or kinetic energy. Potential energy is stored up energy. It has the potential to have a certain amount of energy, right? We usually think of this as relationship to the ground. It's usually not an object that's moving. Potential energy is an object that is not moving, but the higher off the ground it is, the more potential energy, because if it were to move, it's going to have more energy. Kinetic energy is when an object is in motion. So for example, remember that work is done when something is moving, right? So for example, this guy over here is going to have potential energy, where this one is actually having kinetic energy. That kinetic energy means that object is in motion, and for work to be done, it needs to be in motion. So this works, right? This equation is going to come in handy, because remember that triangle, that delta, right, signifies the change. So when we're changing the kinetic energy, right, when that object is moving, that is also considered work. Doing work on an object gives it kinetic energy, right? That's exactly what I was just saying. Kinetic energy is when an object is moving. When you do work on an object, you are moving that object, causing that object to move. So these two, work and kinetic energy, go hand in hand. Okay? Do you guys need more time writing this down? No problem. No rush.
Okay, I'm done.
Perfect.
Okay, you can move on.
All right. So work cannot be perpendicular to the direction of movement. So this is my exact example that I started off the class with, right? So a person is moving at a constant velocity. So remember, the force is acting up on the object, right? When you lift up the box is no longer moving, it's in your arms, but the force is still going in the vertical direction, right? In the up direction. But then this individual is walking across the floor. So the displacement is actually going horizontally. This is a perpendicular motion, meaning there is not work that is going to be done in this scenario. Okay? It was work when he was lifting up the box, and the box was moving in the same direction of the force, right? The box was moving up as he was applying that force up. But then when he started walking with it, the force and the movement were no longer parallel. So therefore, there was no work being done. You guys want to draw this model down? Might be helpful. Kind of just remind yourself, right? Notes are supposed to be for when you get stuck, you look at your notes. So having drawings and visuals are always helpful. Okay. Let me know.
I'm done.
Perfect. No rush.
Okay, I'm done too.
Perfect. Okay. So let's take a look at these different examples. Is there work or not? So in your notebook, decide in which scenario work is done and where it is not. So let's take a look. We've got someone pushing a box. They are pushing the box in this direction, and their motion is in this direction. So is there work being done?
Yeah.
No.
There is. Yeah, so remember that, that's okay. Remember that the direction of the force should be going in the same direction of the motion. This individual is pushing a box across the floor, meaning the force is being pushed the box, making it going to that direction, and it's moving in that direction, right? Abby.
Well, like,
Oh, it just muted you back.
okay. But like you can hold a box and move it, but it's
And-
no work.
Correct.
But you can push it and there's work.
Correct. Because remember, it has to do with the force. The force and the movement has to be in the same direction. So if you're pushing a box instead of picking it up, you're pushing a box, you are pushing it in that direction and it's moving in that direction. Therefore, work is being done. But if you're picking up a box, right? If you're picking up a box, that force is going in this direction. But if you're walking, the force and the motion isn't going in the same direction anymore. So remember that the force and the direction need to be the same. Does that make a little bit more sense? Yeah? Okay. So then let's take a look. This person has a backpack on and is walking across the floor. Is their work being done?
Yeah, because it's going to the right, or
Well, if they have this backpack, which direction is the force on the backpack?
it's going to the side, or I don't know.
Well, when we pick something up, when we have a backpack, right? If we were to make a free body diagram based off of this, so we have a backpack on, we are holding it up by creating the force to go vertical, right? But if we have the backpack, we're holding it up, forcing it to be vertical, but then we're walking horizontally. Is the force and the direction in the same way?
No.
No, right? So let's take a look at these arrows. The direction of the force is going up, right? Meaning it's holding up that backpack, but the direction of the motion is not going in the same direction, right? It's the same scenario with picking up the box and holding it and walking across the floor. That make a little bit more sense, Madeline?
It does, but I'm just like a little bit confused. Like the backpack is still on you and it's still going to the side. Why doesn't that count?
Because the force is not going to the side, right? The force is picking up the backpack. You are using vertical force to pick up the backpack.
Oh,
But you're not pushing, you're not applying force sideways in the same movement. Yeah, I know it's a little tricky. That's why there's a little bit of like, you have to kind of picture it to really get whether or not there's work. So let's look at this third scenario, right? Somebody who's picking up a bag of groceries off the floor. Is there work being done in this scenario?
Yes.
Right? Yeah, because we've got the direction of the force. This person is picking up the bag upwards, and the bag is moving upwards. So therefore, the direction of the force is going in the same direction of motion. Therefore, it is doing work. What about this last scenario?
it's not.
Correct.
It's picking it up like the backpack.
Yep, exactly. So the bag is no longer moving, right? The person is moving. There is force that is putting up in the vertical direction to hold those bags up and not having it fall. But the bag is not moving up. The bag is moving sideways, and that's not work. Okay. How we doing with this so far? Starting to get the hang of it?
Wait, so you said for number 3, that was that not, or was that?
It was. This one, it was work.
Okay.
Right? Because the bag is moving up and the force is going up.
All right.
Therefore, the work is being done. So let's take a look. So yep, there we go. There are answers. Yes, no, yes, no. We've got yes, they're going in the same direction. No, they're perpendicular. Yes, they're parallel, going in the same direction. No, they're perpendicular. So drawing arrows of the force in the movement is going to be really, really helpful to determine whether or not work is being done. Okay? Right. So let's go ahead and do some math projects, some math problems, okay? So these are from our workbook. So we can do these. You can open your books to page 126 if you want to take a look. I'll give you guys a second to get your books out. And open up to page 126. So a car jack exerts an upward force of 5,000 newtons on a car as the car is raised 15 centimeters. How much work is done? So let's go ahead and list out our givens. What do we know already? What information did they give us?
Wait, I have a question. What's the equation? Is it like the W?
W equals FD. Work equals force times distance or displacement. Okay.
So we know the force and the distance, right?
Great. Yep, we do. What was the force?
5,000 newtons.
Good. And what was the distance?
15 centimeters.
Great. Yep, you got it. And so what's the unknown? What are we trying to solve for here?
The work.
Yeah.
So would that be multiplication?
You got it. What are we multiplying?
5,000 times 15.
Yeah. You got it.
So the answer is 75,000.
Yeah. But 75,000 what? What's that?
Newtons.
Close. It's newtons times meters, right? So it's going to be what?
Joules?
Meters.
Joules. But you just reminded me. So it's actually newtons times meters, right? So let's take a double check our equation. In meters. So in order for us to use this as joules, we actually have to change our centimeters into meters. So let's go ahead and take a look at this again. So if this is 15 centimeters and we needed to convert it to meters, what would it be? And this is important to do.
Is it 0.15 meters?
Yep. You got it. Yep, because there's 100 centimeters in 1 meter. So if we wanted to convert it, we would have to divide it by 100, and that would give us 0.15. Perfect. So now let's do that calculation again. Now that we have it in the correct unit, 0.15 times 5,000. What is that going to be? It's going to be a different decimal place. So it's not 75,000, but it's
750.
750.
So,
okay.
Wait, but why do we have to convert it? Like, how do you know to convert it since it doesn't say meters on the problem?
You're right. So that because it doesn't say meters, you need to convert whatever that distance is, you'll need to convert it to meters. So in this case, they told you it was centimeters. Now, the reason I knew to convert it was because I knew that joules is equal to newtons times meters. So in order for me to appropriately use the unit joules, I need to make that distance into meters, not centimeters. So I noticed that I needed to convert it only because it wasn't already meters in the problem. Does that make sense?
Okay, and what is joules? Like, that's like the answer to the newtons or whatever?
Yeah, so joules is just a unit that was created. I know it's a little confusing because you were kind of asking about this in the last unit when we were doing like kilograms times meters per second, right? You were like, okay, but is that the unit or is it something else? And so you were kind of getting to that in the last one. I don't know exactly when they decide what unit is equal to what, like when they keep it raw or when they create a new unit. But joules is newtons times meters. And it's just a measurement to work with, to represent work. We usually use joules to represent energy as well. And it's really just telling us that this amount of force was acted on over this period of over this distance, excuse me. During this distance, actually, I should say. It was during, not over. So it's just one of those things that you might just want to make a note that we use joules, and joules is equal to newtons times meters. Therefore, the distance must be in meters. So even if they were to give it to you in feet, you would need to convert the feet into meters before you could use joules. Does that make sense? It's kind of one of those silly things, but important to pay attention to, because then you change the entire value, right? 75,000 joules is very different than 750 joules, right?
Yeah.
We want to be careful with that. I almost missed it myself, so I hope I didn't confuse you to it that much.
No, I kind of understand it now.
Okay, good. Abby, any questions about that? No? Okay. All right. So good work, you guys. We did figure out that the answer was 750 joules. We figured out that we need to do work. We know the force. We know the distance. So we just need to convert that distance, and we are good. All right. So again, really quick little paying attention here. We need to change this to newtons. Already noticing that they're talking about kilograms. So we'll do that in just a second. But it says a woman lifts a 1.3 kilogram book from her desk and sets it on the shelf that is 0.85 meters above the desk. How much work did she do? What are our givens? What do we already know?
We know the distance, and
Yep.
is that it?
And we need to find out one more thing. What else do we need in that equation?
We need the force.
And so it tells us the mass, right? We know that this book is 1.3 kilograms. What do we need to do in order to find out what the force is? Do you remember from last quarter? We have to multiply it times something. What is it?
I don't remember.
Okay. Abby, do you remember? No. So remember that there is a force acting on this book, right? So what is the force that's acting on this book? Why is it not able to just fly away into outer space?
Gravity.
Gravity, right? Gravity is putting a force on all of us. And therefore, in order to find out what that force is, what would we need to do? We would need to multiply it by something. What would we multiply it by?
1.3.
We will be multiplying 1.3, but by something else. What does that acceleration do to gravity, the one that we've been using all along?
9.8.
Yeah. Yeah, so we're going to be multiplying 1.3 times 9.8 in order to solve for the force. So what is 1.3 times 9.8? Do you guys know?
$12.74.
Yep, you got it. So 12.74 is the force, right? So then what's our distance?
0.85 meters.
Yeah, and it's already in meters, so we don't need to convert anything for that. We already know that it's in meters, so we don't need to do anything to that number. So now if we're trying to find out how much work she did, what's our equation going to be?
Multiplication. So
Yeah.
12.74 times 0.85.
Yep, you got it.
And then that equals 10.829.
Yep. And that's going to be how much work you do. So what's the unit going to be for that?
Joules.
You got it.
I have a question.
Sure.
Why didn't we multiply? Oh, it's because they gave us the mass. Oh, never mind.
Yep. So we needed to find out the force using the mass. You got it. Good. Okay, so are you getting the hang of it a little bit more now? All right, let's take a look at the next slide then.
Wait, so anytime they give you the mass, you have to multiply that by 9.8.
Correct.
Okay.
By the force. Yep. Exactly. Good. Okay. Angled forces. So work is only done in the direction of motion. So even if you're pulling something across like this, okay? So if you have a wagon, if the wagon is moving, it's covering a distance. However, that force is still not parallel. So therefore, even though you're exerting yourself, this does not count as work because the force is going up in an angle, right? So it needs to be parallel to the direction in order for it to be considered work. Does that make sense? Okay. So you can calculate work even if the direction of the force is not parallel. Are you guys familiar with trigonometry before I go into this? Are you guys familiar with cosine, sine, tangents?
No.
I learned about it a little bit last year.
Okay. So really all you would need to know, you won't need to know this equation. It's good to know in general because it just helps when you're trying to solve for things. But even though technically work is not being done, we can't consider this as work being done. We can still, there is movement, there is a force. We can still calculate some sort of work, even though we wouldn't consider it, right? And that's by taking our equation and then multiplying it by cosine. Now, cosine theta, and then the theta is the Greek symbol that we use to represent an angle, right? Oftentimes we'll put a theta there if we're trying to solve for it. Now, we're not going to get into the weeds of trigonometry. Cosine is something that we use. It's a function that we can use to solve for missing angles and missing sides of triangles. Really helpful when you're trying to do something with measuring something at an angle, if you're trying to find the displacement, the trajectory, these things really help with cosine. But I'm not going to go into like cosine exactly what it is. Just know that if you're being asked to find the work for something that is at an angle, you'll use cosine theta, meaning in your calculator, if you have like a graphing calculator, or even if you turn your calculator on your phone to the side, there's usually a cos option. So you would hit the cos button and then type in the angle of where the force is coming from. Does that make sense?
Yeah, I feel like I learned a tiny bit about it in geometry last year, but I don't like anything.
Yeah, I personally love trigonometry. It was like my favorite type of math, but I cannot teach it. So that's why I'm like, I know I could tell you that it's adjacent over hypotenuse, but I don't know if that's necessarily important for physics. Just need to know it. Just need to know this equation. Okay, so relating the two work equations. So when we're talking about these two, right? So when the force and motion are in the same direction, the angle is 0, right? Which makes sense because if work is being done, the applied force is going to be in the same direction of motion. Therefore, there is no angle. It's 0. So the cosine theta would equal 1, which is why we don't always include it because it's just multiplying it by 1. Again, you don't need to know the whole nuances of cosine. Just know that if you do cosine 0, that is equal to 1. Therefore, if you were to plug that into this equation, it would just be times 1, which means it would be whatever force times distance is, which is why we don't include that cosine in there. Okay, so what is the work being done on this object? So if we're trying to solve for the work, we know that the equation is W equals FD times cosine theta. Theta meaning this angle at this point where the force is being applied. So we are given that the force is 50 newtons. We know that the angle is 30. And we know that the distance is 30 meters. We'll check our units. We already have it in newtons and meters, so we don't need to convert anything. We don't know work, so that's what we're solving for. Our equation is that W equals F times D times cosine theta. So let's go ahead and try to solve that. So how would you put that into your calculator? And if you don't have cosine on your calculator, then you can try to look it up on Google. I think if you just put in cos and then in parentheses the number, you can find it. Or you should be able to have it on your phone.
I
Mhm.
got 1,299.04.
Okay, let's take a look. What did you put into your equation?
I did 50 times 30 times cosine 30.
Yeah. Okay, 50 times 30 times cosine 30, which is equal to 1,300 joules. Isn't that what you got, Abby? Oh, you got a bigger number, eh?
I didn't round up.
Okay. But you still got close to it, yeah?
Yeah. I mean, technically, if I would have rounded up, then yeah, I would have gotten that.
Perfect. Maddie, how about you?
I'm not sure.
Okay. That's okay. What are you not sure about? Where did I lose you?
Well, what exactly does cos? Is that a 0?
It's a theta right here. So that just means angle. So you know how the triangle, the delta, the German delta, not German, Greek delta, that triangle, I told you how that represents the change in, and then this represents an angle. So that's often the symbol we use when we're trying to represent an angle. In this case, this angle right here. Does that make a little bit more sense?
When I put in the calculator, I put cos and then 30.
Mm-hmm. Yeah, in the parentheses.
Oh wait, what is that? Wait, so it says 25.5. Is that the answer? For that part of it?
For that part of it, yeah. And then you go ahead and you continue to multiply it by 50 times 30.
So the answer is 38,000. Wait, I did 25. I did the 25.5 times 50 times 30.
Let's see. So cosine 30 Should be 0.15.
Okay, okay, hold on. Wait, okay, so hold on. Now it's saying when I press cost and then 30, it says, wait, is it cost times 30 or just cost 30?
Cost 30.
I got 900. So if I do wait, hold on. If I do cost times 30, well, I'm like, what am I doing?
No, it should be. Yeah, it should be about 0.86.
I don't know what I'm doing wrong.
It might be your calculator because sometimes it like depends on if it's like radians or not. But
It's on my phone.
Yeah, I got 0.86 or 0.87 if you round up. Wait, let me try it on my phone.
I'm really confused. Like, what is the first step? So am I starting with like 50 times 30 M and then I do times 30 costs or
Cost 30. Yeah.
gross 30?
Yeah.
Is
Do
it?
you have like a calculator? Because my phone is being really weird with it.
I got 45,000.
My phone, when I press cosine, it doesn't do cosine. It just does 1. It just doesn't do anything after that.
Let's move on because I don't know how much this is going to be in. I don't know how often this is going to be in your work, but let's come back to this so I can just get a solid answer for you. I'd rather get pause on that question than give you an explanation and then have to come back and then correct my own explanation, and confuse you guys further. So let's pause on that. I'll double check on that just to make sure about what's going on and if that's something that we're going to need to use, that we're going to use a lot in the unit. But regardless, remember that force means acceleration, right? We can still go through it and make sure that we're understanding. Acceleration means increasing velocity, kinetic energy. We're introducing a new equation. So we haven't learned about energy yet, but this is the equation for kinetic energy. Remember that kinetic energy is movement. When an object is moving, we can calculate the kinetic energy. And that's by doing 1/2 times the mass times velocity squared. And that shows that if velocity increases, kinetic energy is going to increase. So the more an object moves, the more kinetic energy it's going to have. Okay, are there any, I know that we're going to come back to this cosine, and I'll come back with that tomorrow to a small group with an explanation. But are we good with it when it comes to like work in general and understanding that the direction of the force is in the same direction of the movement and that equals work? Okay.
Yeah, I think I get that.
Good. Okay, so let's leave that at that. We'll come back to this whole cosine business, but we're going to now talk about power. So power is related to work because it's the amount of work that is being done over a unit of time or over a period of time. So now we're introduced this second equation today. Our second equation is P is equal to W over delta T. Remember that delta represents the change of, right? We're coming back to this delta. So that means that over the time, so if somebody is lifting a box faster than the person next to them, are they going to be doing more or less work than the first person? Right? So that's what we're going to start to think about. Understanding that power is the amount of work you do, but how fast you do it. And the unit that we use for power is watts, which we know we've heard of this unit watts before. And what do we usually use the unit for watts in our everyday like household appliances, or not even appliances, household items? Do you guys remember? Are you guys familiar with what we use when we talk about watts?
Isn't that electricity?
It really has to do with the light bulbs, right? When you're going to buy a certain kind of light bulb, you really need to know what kind you're getting, what wattage, because that's going to tell you how much power is going to be going through, how much work is going to be done over a period of time. Okay, let me know when you guys have this written down on your notes, because you're definitely going to want this written down.
Yeah, I have it written down.
Perfect. Madeline, let me know.
I just took a picture of it, so.
Perfect. Okay, so now we're going to be using a second equation. So there's going to be a little mix of knowing how to solve for watts as well as knowing how to solve for power. So we're going to go ahead and practice this. So a girl does 250 joules of work in 12 seconds. How much power does she deliver? So what are our givens, right? So what are we starting with? What do we already know?
She does 250 joules of work.
Good. So we know work, W equals 250. What else do we know?
Time.
Time, right? And so if we take a look at that equation for power, right? Power is equal to work over time, right? And we're know what's the unknown? What are we trying to solve for?
We're trying to solve for power.
Right. So we're trying to solve for power. So what's our equation going to be?
Is it 250 divided by 12?
Yeah, you got it. That's right.
So 20.83.
Yep. You guys got it. Good job. Okay. So for the last problem for the day, it's going to be a little bit of a challenge. So we've got a couple of variables that we're working with here. So let's talk about this equation first, because I know it can be a little confusing considering the fact that we're going kind of back and forth between equations. So remember, first of all, the problem is asking a crane must lift a 48-kilogram load to a height of 3.2 meters. The load must be lifted in 11 seconds at a constant speed. How much power is needed? So let's take a look at this here. We have our equation for power. Power is equal work over time. We also know that work is force times distance. In this case, the height, right? So we know that the distance that we're talking about right now is the height that it needs to go. We're giving it in kilograms. So we've got this mg. So force is equal to mg, right? That's how we figure out what force is. The mass times the gravity due to acceleration, which you guys know is what? What is that gravity unit or number?
9.8.
That's right. So now to do this entire equation, we can combine it, right? This is equal to that, so we can just replace the W with the equation for work, and that's going to be the mass, 48 kilograms times 9.8 times the height, just 3.2, over the time, which is 11 seconds, and that's going to give you the power that you would need. Go ahead and tell me what that is when you get your answer.
How does the height go into the equation? Since we have the weight and then the speed to the seconds.
Yeah.
What about the height? How does that does that go with like the weight?
Yeah. So over here where it says work, so remember that the equation for work is force times distance. In this case, the height is the distance that it's traveling. And then in this equation, we just broke down the equation for force to equal mass times gravity, right? Which is how we find out the force. So it's really just the height is the 3.2, that is the distance. It's just because it's going vertically that we can call it the height.
So do I do 48 like times 3.2?
Times, yep, and then you have to multiply that by one more thing, which is gravity, right? Because 48 is the mass. We need to find the force. So to find the force, we're going to do 48 times 9.8 and then find that answer out and then multiply that by 32. And that's going to give you your work. And then you're going to want to divide that by the time to find your power.
Okay, and so then I do 1,505 divide by 11 seconds.
Mm-hmm.
So I got 136.84.
Mm-hmm.
Okay.
Yep. And then what's the unit for power?
Not sure. I don't know.
You took a picture of it.
Joules per second.
Yep. And then that is equal to joules per second is the same thing. We can
Watts.
Yep, you got it. Yeah, you got it, guys. That's everything I have for you. The only other thing I was going to show you was this this picture of a concept, and so the relationship between work, energy, and power. And that basically you've learned about work, you've learned about power, which is 2 out of the 3 main concepts for thermodynamics. So you guys already understand 2/3 of thermodynamics, right? So this is just a really quick way to give you an understanding, a visual representation of what it is, how it connects, and examples. Okay. Other than that, that's everything I have for you.
Okay, thank you.
You're welcome. Please let me know if you have any questions. Other than that, we're all set. You're free to go.
Okay.
Yeah. Have a great day, you two, and I will see you tomorrow.